Hello, in this video I'm going to continue talking about collections of fundamental particles by talking about atoms. Now, I'm not going to be going through here the evidence for, why is the atom structured in the way that it is and things like that. I'm putting that in a separate video. Here I'm going from the idea of, well, we know what an atom is, as in we know that there's an atomic nucleus which is small and positively charged, and that is surrounded in some fashion, which we'll talk about, with negatively charged electrons. So we've got the positive in the middle and we've got all these negatives floating around the outside in some fashion. So let's try and get a clearer picture of exactly what's going on here and why certain things aren't happening, which is quite often more interesting when it comes to atoms. So I mentioned briefly in the previous video that when you're just looking at the nucleus, so if you zoom in on the nucleus and we've got all these protons and neutrons, which are all bound together. So we've got lots of neutrons, which of course have no charge, and we've got lots of protons, which have all got this +1 electric charge. So we've got more than one force in play because the protons are going to be repelling each other from the electromagnetic force. So there needs to be a stronger force, and strong is the word because it's the strong nuclear force that's holding them together. So they're repelling with the electromagnetic force, but they are attracting using by engaging in the strong nuclear force. And it's the same with the neutrons. I mean, the neutrons don't have anything else which is going to be holding them in here in the nucleus. The only force they've got available is this strong nuclear force. So that's putting certain limits on what's going on in an atomic nucleus. We know that the strong nuclear force only acts over short range, over this sort of 10 to the minus 14, 10 to the minus 15 meters. So once we've gone beyond that, and in fact, even when we've got to this 10 to the minus 14, we're already struggling here with the strong force to provide enough glue, as you were, for holding everything together. So this is putting an upper limit on the size of a nucleus of an atom. So that is something. But we've also got the way these things are arranging themselves. We're not seeing just any old combination of protons and neutrons out in the world. When we're looking at atoms, so you look at the periodic table. Now, the periodic table is by and large arranged by the number of electrons in the neutral state of the atoms, so which is the number of protons inside the nucleus. Because from the chemistry point of view, it's the electrons that are describing the behavior of these different elements. But we're not just getting, oh yeah, well, if you've got hydrogen, so we've got one proton sitting there, oh well, the neutrons, let's just add in 20 neutrons then, because they're all going to attract with the strong nuclear force. We're not adding in electromagnetic propulsion, so we can have this massive hydrogen nucleus which has still got a charge of +1. Well, we don't see that. Okay, we might go to deuterium or tritium, where we'll have 1 or 2 neutrons added in the mix, but we're not getting this. By and large, we have got a stable isotope of a particular element, which has got a certain number. Obviously, the number of protons is fixed, but we'll have a certain number of neutrons, which is giving us our most stable structure. If we've got more neutrons or fewer neutrons, then this is when these isotopes become radioactively unstable, and they will decay in order to go to a more stable state. So what is it that's affecting this stability? Why can't we just keep on relying on the strong nuclear force here to keep building this up? Well, surprise, surprise, this is coming back to quantum mechanics again, and our Pauli exclusion principle. So the Pauli exclusion principle has already been great in the fact that it's allowing us to create this matter with structure, because the Pauli exclusion principle is saying we can't have the same types of particle in the same quantum state at the same time. So they're essentially making things take up space, and that's why we're getting this solid matter. But they have something else that they're saying as well, and this is coming back to spin. So we know that these are all fermions. They've all got this half integer spin. So if we've got half integer spin, we can have what is we could have a up spin or down spin is what is known as. So we could have plus a half, we could have minus a half. So let's take those as an example. Now, if you're putting two protons or neutrons, so I don't know, let's go with neutrons. You've got two neutrons and you want to try and bind these things together. You think, okay, this is great. We've got the strong nuclear force here. Let's go for it. Let's bind them together. Well, it turns out when, as described by quantum chromodynamics, which is describing the strong nuclear force, that if you want to get these two particles into their most stable state, then you want them to have the same spin. So there's nothing in the Pauli exclusion principle which is saying, oh yeah, well, we can't have an upspin and a downspin neutron. That's fine. You can have those trying to bind together because they're not occupying the same quantum state at the same time. One of them's got upspin, one of them's got downspin. That's great. The trouble is they don't bind well enough, according to the description of quantum chromodynamics, in order to make it stable. In order to get stable configurations, you want to have aligned spin. And that means we can't have two neutrons. We need to get rid of one of those neutrons and then put a proton in. And we can put a proton in to have aligned spin because they're now different particles. So they're not clashing with the Pauli exclusion principle. They're not excluding each other. So the only way we're getting these baryons, these protons and neutrons, baryon, collection of three quarks, the only way we're getting baryons to bind is if they've got aligned spin. So that means we need protons and neutrons. And that is why we're getting, certainly for the lighter elements, you're getting similar numbers. You're not drifting enormously from having the same number of protons and neutrons. Now, there are other factors at play here. I mean, you don't always have the most stable state as you get exactly the same number of protons and neutrons. There are a lot of complexities to how these things bind together. But essentially, that is why, at least the main reason at the basic level, why we can't just bind together a whole load of protons or a whole load of neutrons is because of what's going on here with the spin. And then, of course, that says a lot about what's going on with the isotopes as well, of why you're getting these different configurations of atoms. The other thing that can be weird when you think about it with atoms is what is going on with the electrons. I've already taken up a lot of the screen here, so let's change over to red anyway. I mean, we've got this positively charged, dense nucleus. It's in a small space, and we've got this negatively charged, much smaller electron. The electron doesn't engage in the strong interaction because it's a lepton, it's not a quark. So the force that's at play here, which is dominating everything else, is the electromagnetic force. And with the electromagnetic force, well, the electron is attracted to the nucleus. We've got a negative charge and a positive charge. So why doesn't the electron just smack into the nucleus? And why don't we end up with what looks like this plum pudding model that was proposed tentatively? He was never really committed to it, by J.J. Thomson back in the day, where you've got this lump of positive charge with these sort of raisins of electrons dotted around. So why aren't the electrons constrained to the size of the atomic nucleus? Right, this is getting us onto another idea, fundamental idea of quantum mechanics, and this is the Heisenberg uncertainty principle. Hopefully I've spelt that right. I might not have done, as to whether I got the E and the I the right way round, and whether he's an E. I think he's an E rather than a U. So yeah, Heisenberg uncertainty principle. Don't quote me on the spelling. So the Heisenberg uncertainty principle is placing a lower limit on what we can know about the position and the momentum of a particle. So there's a lower limit going on there. We can't be certain about things. So we've got this uncertainty principle. We never know for definite where something is and how it is moving. If we know where something is, we don't know how it's moving. If we know how it's moving, we don't know where it is. And there's this sort of fuzziness about what we can say about things. Right, so how is this affecting what's going on with this electron here? Turns out if an electron, if you constrain its position to the size of an atomic nucleus, then it has a certain momentum which has to be associated with it. Now, if a momentum, we know that momentum and force, let's talk in the language of classical physics here and talk about forces rather than interactions. To constrain a particular momentum, in order to get that momentum to be changing quickly enough that position is going to be constrained to a small area, you need a high force. Now, the protons have this because they've got, and the neutrons, because you've got the strong force. The electrons are working with only with the electromagnetic force, which is about 1,000 times weaker. So you can't constrain the momentum to such a small volume as an atomic nucleus for an electron. There's a fuzziness in what we can say about it. So if you try to constrain it, say, well, actually, we've got a certain amount of momentum, that means it's going to break out. And it's got to be a certain distance. We've got an uncertainty in its position. And that is why the electron isn't inside. It can't be constrained to the atomic nucleus because of the Heisenberg uncertainty principle. There's an uncertainty, a fuzziness about what we can say about the position of the electron based on the momentum that it's got, and vice versa. So yeah, it's just too weak a force, the electromagnetic force, to constrain an electron by that amount. So that is why we have these shells of electrons. The electrons then arrange themselves in certain ways, similarly to how the protons and neutrons are arranging themselves inside the nucleus, according to rules of quantum mechanics. The electrons will then arrange themselves around the nucleus, outside of the nucleus. They will then arrange themselves, again, according to the rules of quantum mechanics, arranging themselves in certain ways. Some ways are more stable than others. And that starts getting into these shell structures that you see in chemistry, although we touch on it in physics as well. But this is really getting into the world of the chemist. So that's a few things that might not make sense otherwise with atoms as to why they are arranged in the ways that they are. You can't just start building up massive lumps of neutrons or massive lumps of protons, and why we don't have the electron just falling into the atomic nucleus. So yeah, there's a lot going on behind all of this in why atoms are structured in the way that they are. And that's why you've got all of these detailed theories inside quantum mechanics for describing all of this behavior. But yeah, once we've got beyond this level of aggregating up these particles, we've already aggregated fundamental particles from quarks up to baryons, and then from baryons up to atoms by bringing in leptons. So we've gone quark to baryon, added in leptons to get atoms. Now we're moving into where you're combining atoms. That's going into chemistry, because we're really now looking at, well, what are the electrons doing? Which is the big question that every chemist faces on things. What are the electrons doing? How are they then creating big structures in sort of lattices and crystals and things like that? How are they combining into molecules, and then how are those combining? And that's where we're getting the two areas of organic and inorganic chemistry, which I'll touch on in a later video. So really, our aggregation of fundamental particles in physics is pretty much stopping at the atom, and then we're going to leave the rest to chemistry. Although we do come out the other side that, of course, once all of that has aggregated up into macroscopic matter, then we're into the realms of classical mechanics and we're back into physics again. So the chemists are sitting in that space in between the quantum mechanics and classical mechanics, and the chemists do their work in there, and we just pick up what happens on either side of it as physicists.